Hi, welcome to the calculus of inverse functions. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. We're using Larson's 11th edition calculus text at UTEP for Math 1411 Calculus. This comes to us from Chapter 5, and in particular, Section 5.3, Inverse Functions. So if you need a review of inverse functions and what are they and how do you find them from pre-calculus, you could check out my notes or my videos from Math 1508 Section 1.9. In this video, I'm only going to talk about the calculus aspects, but I do have a lecture called, funny enough, 1508 Sec 1.9 Inverse Functions, and you can find that on my YouTube channel if you need any review. We know from algebra that only one-to-one functions have inverses. But how do we know functions are one-to-one? We could graph them, but unless we know some pretty specific information about the function, we don't know if we have a very good representative window on our graph. We could assume the professor wouldn't lie, which I would like to say is always a good bet, but you never know. The only safe bet is to use calculus. Calculus can tell us when a function is one-to-one. So, a definition, a function is monotonic if it never decreases or if it never increases. That does not mean it's constant, one or the other. That is, if it has one direction. If a function has a first derivative that's always positive, or if a function has a first derivative that's always negative, then we know it's monotonic, and so we can say for certain, hey, this function is one-to-one. For example, we could show that the function f of x equals 4 over x squared on the interval from 0 to infinity is strictly monotonic and therefore has an inverse on that interval. And so what we would do is we would rewrite f of x equals 4x to the negative 2, take the derivative, which of course is negative 8, x to the negative 3, rewrite it. The negative 8 is just a negative number, but a negative exponent tells us to take it to the denominator. So negative 8 over x cubed. And remember, this is only for positive values of x on the domain of 0 to infinity. Negative 8, the numerator, always going to be negative. On the given interval, we know the denominator will always be positive. Therefore, a negative, always negative, divided by an always positive is negative. Our conclusion that this function is always decreasing on the interval, therefore it is strictly monotonic. All right, get the idea? Okay, so what can we do with this new knowledge? Let f be a function that is differentiable on an interval I. If f has an inverse function g, then g is differentiable at any x for which the derivative of the function evaluated at the inverse is not 0. Moreover, the derivative of the inverse is the reciprocal of the derivative evaluated at the inverse of our x value. Assuming, of course, the denominator is non-zero. Now, that is a bit confusing. Write this down. Right? Use the f inverse notation if you prefer. If you want to call it g, that's fine. Hit pause. And welcome back. Examples. Let's verify that f has an inverse. Then use the function f and the given real number a to find f inverse prime at a. So if f of x is 5 minus 2x cubed, and a is a value of 7, first of all, we know the derivative of 5 minus 2x cubed is a negative 6x squared, and x squared is always positive, therefore negative 6, it's always positive or 0. Negative 6 times a positive or 0 will always be 0 or negative. So the negative 6x squared is non-positive. It's always negative, which implies monotonic and an inverse exists. Okay, so we know that f has an inverse because it's never increasing. Now, we want 7 to be the input in an inverse. So it has to be the output of the original function. So we're going to solve 7 equals 5 minus 2x cubed. When I subtract 5 from both sides, I'll get 2 equals negative 2x cubed. If 2 equals negative 2x cubed, we'll divide both sides by negative 2, and we'll get negative 1 equals x cubed. And if we take the cube root, we'll find that x equals a negative 1. If f of negative 1 equals 7, then f inverse of 7 equals negative 1. Therefore, the derivative of f inverse of 7 is the reciprocal of the derivative of f prime at negative 1. The good news is, even though I forgot my negative on this, I can't take the cube root of a negative number very well, evidently. The derivative evaluated at negative 1 is the same as the derivative evaluated at positive 1. So we'll have 1 over negative 6 times negative 1 squared. That's 1. That's a negative 1/6 as a result. So without even knowing what the inverse function is, although we could find this one, we can evaluate its derivative at a specific value. Let's do that again. We'll verify that f has an inverse, then use the function f and the given real number a to find f inverse prime at a. So f of x is sine of x, and we're going to use the interval from negative pi over 2 to pi over 2. Some of you might recognize this as the restricted domain for the sine function so that we can take an inverse sine. We're going to use the a value of 1/2. First of all, f prime of x is cosine of x, and on this particular interval, cosine is non-negative, so we know it's monotonic, we know an inverse exists. I want to solve sine of x equal to 1/2, and I know this occurs when x is pi over 6 in this particular interval. So the derivative of the inverse at 1/2 is equal to the reciprocal of the derivative of f at pi over 6. That's 1 over the cosine of pi over 6, which is 1 over the square root of 3 over 2. Take the reciprocal, we'll get 2 over the square root of 3, and then we'll rationalize our denominator to get 2 square root of 3 over 3. Yeah, so non-negative, we know it exists. Solve for the x value that gives us an output of 1/2, and then use our formula accordingly. Last example. If f of x is cosine of 2x on the interval from 0 to pi over 2 and an a value of 1, first thing we'll do is use the chain rule to find the derivative. F prime of x is negative 2 sine 2x, and negative 2 sine 2x is non-positive in the given interval, right? Because sine of 0 is 0, and sine of pi is 0, and everything between 0 and pi, because of the 2x here, take care of that, put 2x, pi over 2 in for x, we'll get pi. Any value in between 0 and pi, sine is positive, but when I multiply it in front by a negative, I end up with non-positive in the given interval. Non-positive meaning it could be 0 or negative. So I want the input of my inverse to be 1, which means the output of my original function is 1. I know that cosine of 2x equals 1 when 2x equals 0, because cosine of x equals 1 at an angle of 0 in this particular interval. So when 2x equals 0, x equals 0, and I will have the derivative of the inverse at 1 is the reciprocal of the derivative of f at 0, which is 1 over negative 2 sine of 0, which is 1 over 0, which is undefined. So even though it has an inverse, we may not be able to evaluate the derivative of the inverse because we might get an undefined value. That's it for the calculus of inverse functions. It's a process, kind of straightforward. Make sure it's monotonic. Then we find our input that gives the desired output. Use our formula. Thanks for listening.